In this lesson, we're going to look at balancing chemical equations and 3 different types of chemical equations that you will be learning about over the next couple days. So the bell ringer today, in physics, you learned about the conservation of momentum. I want you to kind of remember what that means. So we've got like a large object here, it's moving with a certain velocity, it hits a smaller object, and then that object's going to move based on how much momentum the first object had. And we learned that momentum was conserved. So in chemistry, we have a chemical reaction, so we've got a bunch of stuff on the left side, a reaction occurs, and then you've got a bunch of stuff on the right side. My question is mass conserved during a chemical reaction? So we've already talked about the subscript when we're looking at a compound. So here we have aluminum sulfide. We know that the 2 here tells us that we have 2 aluminum ions, and the subscript here tells us that we have 3 sulfur ions. Subscripts in parentheses get multiplied by the subscript outside the parentheses. So we have a 2 here outside the parentheses, so that 2 would multiply with the 3 here, so we have a total of 6 oxygens. The nitrogens have like an imaginary 1 here, and that 2 would also multiply by the 1, so we would have 2 nitrogens here. This 2 does not multiply with the magnesium here, so does not. A coefficient multiplies the number of each ion in the formula. Okay, so in this case, our 3 is going to distribute to our calcium here. It's also going to distribute over here to the hydroxide. So we're going to have 3 calciums. Okay, now we have 2 OHs here. So in this case, we have 2 oxygens, 2 hydrogens, but then that 3 distributes in here. So we're going to have a total of 6 oxygens and 6 hydrogens. Okay, when we go to balance chemical equations, we want to have the same stuff, the same number of things on the left side of the equation as that we do on the right side of the equation. When we go to balance equations, we want to do hydrogen and oxygen last. And when we balance polyatomic ions, we want to balance them as a single unit. In this example, there aren't any polyatomics, but there will be in one of the later examples. So I will point that out when we get there. But when we do these, I find it helpful to create a table. So we're going to balance the hydrogens and the oxygens. And what I'm going to start by doing is kind of taking an inventory of what we have. So on the right side, you can see that we have 2 hydrogens and we have 1 oxygen. Again, there's like an imaginary 1 here. That's on the right side. Now let's look at the left side of the equation. We have 2 oxygens here, and we have 2 hydrogens here. So what I'm going to do first is look at the oxygens, because I realize that my oxygens are out of sync here. I've got 1 oxygen on the left, 1 oxygen on the right, and 2 on the left. So what I'm going to do here is I'm going to put a 2 in front of the H2O, the water, and what that's going to do now is it's going to multiply this. So I now have 4 hydrogens on the right and 2 oxygens on the right. So now my oxygens here are good, they're balanced, but on the left side of the equation, if you notice, my hydrogens are now out of sync. They don't balance. I've got a 4 on the right, a 2 on the left. So I'm going to put a 2 here now in front of the H2. So this now becomes 4 hydrogens. My equation's balanced. What I'm going to do is I'm going to add a 1. Oops, I don't know why that turned to yellow. I'm going to add a 1 in front of the O2 just to remind myself that I've checked that, it's good, and it's balanced. In some cases, you can leave that blank, but I personally prefer to just put the 1 there just to remind myself that I've checked it and I've balanced everything. All right, let's look at an example. So I'm going to start by making my table first. So I'm going to list out all of my ions. Okay. So I've got iron, hydrogen, and oxygen. We're going to balance the irons first because that's our rule. We always do hydrogens and oxygens last. So on the right side of the equation right now we have 1 iron. On the left side we have 2 irons. Again, I'm looking at the coefficients here. There's a 1, like an imaginary 1 in front of the iron on the right. And on the right side here I have 2 hydrogens coming from here. And then I have 2 hydrogens on the left side. Okay. So with oxygens on the right side, again, we have an imaginary 1 here. So there's 1 oxygen on the right, and there are 3 on the left. Okay, so right off the bat, I recognize that there is 1 iron on the right and 2 on the left. So I'm going to put a 2 in front of the iron here. So now this becomes 2. So my irons are balanced, but now I'm going to look and recognize that my oxygens are out of balance because I have 1 on the right and 3 on the left. So I need to get 3 oxygens on the right. So I'm going to write in a 3 here. So now I've got 3 oxygens, but when I did that, my 3 also changed the amount of hydrogen I have to a 6. So I'm going to go to the left side of the equation now and recognize that I need to put a 3 in front of the hydrogen because now I have 6 hydrogens. And again, I'm going to put a 1 here in this blank just as kind of a reminder to myself that I've looked at that and everything's good. Okay. I personally prefer to put the 1s in front just so I know that I've checked everything. I don't like to leave things blank. Okay. If you leave something blank, I'm just going to assume that it's a 1 there. Okay. But again, me personally, I tend to put the 1s there just to remind myself that I've looked everything over and I'm not missing anything. Either way is fine. Okay, here's another example. Let's start by making our table. So we've got carbon, oxygen, hydrogen. Okay, so I see 1 carbon on the right, 3 on the left. Okay, now this gets a little tricky here because we have oxygen here and I also have oxygen here. Okay, so when I write this out, I want to count both of them. So there are a total of 3, oops, meant to put that in red. There are a total of 3 oxygens on the right and there are 2 on the left. Okay, and then I've got 2 hydrogens on the right and 8 on the left. So we do oxygen and hydrogen last. I'm going to start on the right side with the carbons. I need to put a 3 here. So now this becomes 3, 3. Let's try that again. Doesn't want to work. Okay, that 3 is also going to multiply with the 2 here in front of the oxygen. So now I have a total of 6 oxygens here. Okay, and then I need to balance my hydrogens because I have 8 on the left. So I'm going to put a 4 here. Oops. So now this becomes 8. But when I did that, I also added 4 to the oxygen. So now I have a total of, let's see, 6 from the 3 times 2. And then I have 4 times 1. So this is going to be a total of 10 oxygens. 10 oxygens. Okay, so let me explain one more time where that came from because it got a little tricky. So right here, I've got 3 times 2, so that gave me 6, and then 4 times 1, that gave me 4. So that's where the 10 oxygens came from. Okay, on the left side of the equation, I have 2 oxygens, but I need to get to 10 because everything else is balanced. So I'm going to put a 5 in front of the O2 and then a 1 in front of this other blank because, again, it's a reminder to myself that I've looked at it and everything's good. So this becomes 10. Everything's balanced, we're all good. All right, this third example gets a little scary because we've got a lot going on here. We also have a polyatomic. When we work with polyatomics, we want to treat them kind of like their own entity, like they're their own ion, even though there's sulfur and oxygen present. So let's start by making a table. If you have a polyatomic, like our SO4 here, or sulfate, we want to make sure that we treat it just like its own ion, and even though it has oxygen in it, doesn't necessarily mean that we have to deal with it last. So making my table. Okay, let's start by balancing our, I'm going to start from the bottom. I'm going to start with our polyatomic. Okay, so we've got 3 here. On the right side, okay, on the left side here, you have to be careful. So it's SO4, that's the whole polyatomic, right? So even though there's a 4 on the oxygen, don't get confused, this is still 1 sulfate. Okay, I see 1 potassium on the right, 2 on the left. As far as bromines, I've got 1 on the right, 3 on the left, and then for aluminums, 2 on the right and 1 on the left. Okay, so again, I'm going to start by balancing my polyatomics first. So to balance this out, I need a 3 on the left side. So this now becomes 3, and then this is going to distribute to my potassium, so that is 6. Okay. Let's see, aluminums. We have 2 on the right. I need 2 on the left. So to do that, I'm going to put a 2 in front over here. So not only does my aluminum change, but I'm also changing my bromine to 6. Because remember, this 2 distributes to both terms. Okay. So let's see what we need to fix. Our potassiums are out of balance. So to balance my potassium, I need to put a 6 here. This is going to fix both my potassium and my bromine. And again, I'm going to put a 1 in front here just to remind myself that I've looked at that and everything's good. So 6 and 6, everything looks balanced. Sometimes when you're working with sometimes when you're balancing equations, you might have to go back and forth a couple times. So, let's say that my bromines are out of balance. I might have to go back a 3rd time and fix it to balance again. So it's kind of a trial and error. You have to go back and forth until everything's balanced, okay? It's kind of like a puzzle almost. So if you have to go back and balance a couple times, don't get frustrated. You're doing it right. It just takes practice. It just takes a little bit of guesswork to get the right fit. Okay, so we have a couple different types of chemical reactions that you need to be able to recognize and properly identify and predict. Okay, so the first one is a synthesis type reaction. You may have heard the word synthesis before. Sometimes it's used in manufacturing, especially like chemical manufacturing, like you synthesize something. I think they use the word synthesizer in music for like those fancy keyboards that can synthesize different sounds. So it just basically means that you are taking ingredients, combining them, and making something. So in this example here, the top part here is like the general form that our synthesis reactions take. So you have an A plus a B, and they combine to make an AB. So this is almost like our fusion type reactions from nuclear chemistry. You have 2 smaller pieces and they combine to make a larger piece. So that is a synthesis type reaction. So in my example here, I've got sodium and I have chlorine. Those 2 pieces combine to make a larger compound, sodium chloride. Another type of reaction that we have is a single replacement type reaction. Okay, so I'm going to give an analogy for this that is a little goofy, but it's going to help you remember. So if you've seen the Twilight movies, you have a happy couple of Bella, who is the girl, and you've got Edward, the vampire. But then along comes Jacob, the werewolf, who also likes Bella, and he really wants to woo her. So he comes into the picture and basically he knocks out Edward briefly, and now it becomes Bella plus Jacob, and poor Edward is knocked out. Okay, little silly, but you're going to remember it now. So when we have a single replacement reaction, another ion comes in and knocks out one of the ions in the compound to create a new compound, and what gets knocked out is left over. So in this example, we've got copper. Copper really wants to come in here. So copper replaces our Ag in this case, and we have a brand new compound with just copper. So in single replacement, you have a single element and it reacts with a single compound. All right, another type of reaction that we have is called a double replacement. In a double replacement reaction, you are trading places. So we have two different compounds. And my pen does not want to cooperate today. I think my pen is on vacation. All right, so we have two different compounds, and what's going to happen is they are going to swap partners. Okay, so A and D in this case are going to combine. B and C are going to combine. So a couple years ago, there was a show on TV called Wife Swap, and that's essentially what's happening here. You are trading partners. So down at the bottom, if you look, in these cases, we are trading partners, and we end up with two brand new compounds. So in this case, two compounds are reacting. So you should have a practice sheet of problems. I'd like you to work through these. It does take practice and repetition to be able to recognize what type of reaction is going on. So please work through all of these practice problems. And then my exit ticket for today, you don't have to do anything else but tell me what type of reaction this is. Okay? So please look at it carefully, consider it, and then write that down on your sheet. And then, of course, have a great weekend.